recording. So it is my great honor to introduce our speaker, Professor CHOW. Yating CHOW is an assistant professor in the Department of Mathematics at the University of California, Riverside since 2018. He did his PhD at CUHK from 2010 to 2015. And he was a CAM camp assistant adjunct professor at UCLA from 2015 to 2018. Professor CHOW's research interests focus on a lot of things. So inverse problems and ill-posed problems, Hamiltonian-Jacobi equations, optimal controls, dynamics of the nonlinear system, solutions in the mean field, optimization algorithms, and so on. He published papers in top journals like Journal of European Math Societies, JMPA, Journal of Numerical Analysis, and SciAm Journal of Scientific Computing, and inverse problem, and so on. So today, Professor CHOW will talk about resolution analysis in some scattering problems and enhance the resolutions in certain scenarios. The floor is all yours.
Thanks very much for the very nice introduction, and thanks again for the invitation to give this talk. So today what I will talk about is some problems related to inverse scattering problem, and namely that we try to understand resolution either in the global sense or in some localized sense, that we want to enhance the resolution of an image from, for instance, measurement of scattered field from afar. And you realize a little bit discrepancy, perhaps. I apologize for that, in the title I gave is enhanced resolution, but in here I wrote super resolution because it's kind of tricky in a way that, in fact, we are trying to understand and boost resolution, but not entirely sure whether that really entirely qualified as super resolution or not. But these are some of the directions we are heading towards. So this is a direction of study that is going in line with the work that starts from my PhD studies, and also the studies I work on with some of my collaborators in several visits in France and Switzerland. And this is a joint work, several joint work with Professor Habib Ammari at ETH, Professor Hongyu Liu at City University of Hong Kong, and I know that he's probably giving another talk at the same time. So yeah, so he's not here today, but yeah, he's very. I mean, he's a great professor and kind of support this kind of directions well, work on that a lot. And then some of the numerical work also has some origin of from Professor Keji Liu in Shanghai Key Lab. And part of the work that I have been working on is with Professor Mahesh Sunkula, who's currently at Purdue, and at last that's also with my PhD advisor, Professor Jun Zou. Okay, and let me introduce the background a little bit, and then the several kind of directions I want to explore with you. Some of them are still kind of we are still kind of exploring what we can do with what we have known to, for instance, enhance resolution, and we can discuss a little bit. So we are kind of in a situation that we focus on inverse problem, where we want to see an object from some sort of physical measurement, for instance, scattered field, scattered flux, some sort of those kind of quantities like in the far field or like in the near field. And from these data or partial data or full data, we the inverse problem will then be about trying to reconstruct, for instance, the shape, the physical parameter within the background, okay, or within the space, and we want probably to recover them well, okay. So that's the kind of problem we are looking into. For instance, you can imagine a wave propagating from top to the bottom, and then you imagine that those waves kind of hit certain obstacles, and of course they will now get some sort of diffraction, reflection, so on and so forth, and then this kind of disturb the wave a little bit. Now our job is probably hoping to obtain some information about these inclusions, okay, perhaps recovering them fully, perhaps at least getting the shape of it, or perhaps identifying, for instance, the convex hull of the guys shaped by it. Okay, so different forms or versions of reconstructions are the main goal. And one of the things that we notice, or everybody would realize when they work with this, is there's some sort of so-called resolution limit. So the idea, or in a very vague sense, as an example, perhaps you can think of like some sort of measurements from afar. Then from the understanding, you probably have some sort of point spread function in your image that you can recover only to that bit. For instance, some expressions in terms of Hankel functions, and instead of having a point source that you can recover as a point source, now in the image you see some sort of blurry image. Okay, and because those blurry image are those kind of point spread functions, you can imagine your reconstruction somehow like a convolution of these guys. So if they are too close, it's very difficult to distinguish them. Okay, that's the idea. So for physical relevance or numerical relevance, if they are kind of too close, then they just look like one bump, even though they might be coming from two points. And one thing that you can imagine before we move on is, for instance, if you look into the far field, or the so-called the case that you get a certain limit and of the radius, okay, to infinity, and then you get the far field pattern. What you can imagine is the limits, or the resolution limits, would be more or less like the half of the wavelength. Okay, that's somehow the Shannon sampling theorem. Okay, and so you can kind of imagine, if there's nothing, okay, I mean there's no super resolution or nothing, then what you can imagine is somehow like half of the wavelength when they are afar that you can recover, and then when the skies start moving close, they start to enter the near field region, and then you can resolve more and more, and then perhaps when it comes to very close to you, then you can resolve way better than from afar. Okay, there's actually some work with Keji that we have done on that, but that is not something we will show today. But that's the idea. Okay. Now, there are many works that tried to break the resolution limit. Actually, some of the new ones would be, for instance, doing the bubbling and so on and so forth. Or, but one of the first several works would be from Professor Bao Zhang and Li Peijing, Professor Li Peijing, on near field imaging, and other, sorry, Professor Bao Gang and Professor Li Peijing on some of the near field imaging, and of course there are also Professor Ammari's work and some of the physicists' work on the Fink and other people on sub-wavelength resonator, and moving along that side, we also have Professor Zhang Hai's work along that line. And there are other directions where we have Professor Hell and other people on the single molecule imaging. So in our discussion, we would want to understand on several fronts how we might be able to get better resolution. One of them is very interesting because it's somehow naturally occurring without any kind of techniques, but it might be a little bit of coincidence, which is that at some chosen high contrast targets, or you can imagine that you have an inclusion and then the coefficient is suddenly very high at that bit. If the high contrast is fitting certain pattern, then we realize that there's actually some sort of high resolution that you can recover the shape of the obstacle without any techniques. Okay, so that's one direction we would be exploring. And then we will also realize that curvature of the inclusion will affect the resolution. And we have a way to quantify this kind of local resolution analysis at high curvature, that perhaps you can imagine what's going on is if you have an object and there's a corner, like sharp corner, then light shining through it, you will see the reflection to the eyes, and this is kind of shiny. Okay, so this somehow give us an idea that perhaps there are some sort of high resolution when there's very high curvature around the point. And then we also want to look into resonance modes, and resonance modes are very much related to the resolution analysis, because those resonance modes actually enter the measurement as some sort of resolvent operator. Okay, and then in the end, we will also, if we have some time, we will also discuss an idea called transmission eigenfunctions, or what we introduce as almost transmission eigenfunctions, where we somehow see certain kind of localization or concentration on the surface. Okay, so these are some of the things we would discuss. And just to come back to our setup, the idea is we are, well, actually, we can go a little more general, but in this talk, I will probably focus on a Helmholtz type equation, where that would model, for instance, transverse electric or transverse magnetic kind of scattering, where we will have the divergence form acting on 1/mu, okay, gradient u, okay, plus certain frequency omega square, okay, times another coefficient, and one is the permittivity, the other being the permeativity. In fact, in many of the analysis, it is very similar to the case when you only have a Laplace u plus omega square times a certain parameter, describing the physical constant. Okay, so I mean, there are a little bit difference, but not so much difference. And the fourth problem that we are looking into is that given these coefficients, or given the domain, we want to compute or understand the wave, or the scattered wave, or the flux or whatever that comes from this model. Okay, so it is like we kind of put in an incidence ray, then there's some sort of inhomogeneous domain, not entirely really a scatter, so we don't have the sounds of hard in our discussion, but it is an inhomogeneous medium, and then it's kind of getting the field scattered, and we measure it on the boundary. And the fourth problem will now be understanding the PDE. Okay, but that's kind of well understood. So we move to the inverse problem, and the inverse problem will now be that given the measurements of the scattered field, for instance, along the boundary, or some sort of far field pattern, which is like the scattered field with the limit, are we able to recover what's inside the space, for instance, the inhomogeneous inclusion. And since our talk here is not about reconstruction methods, we can, for instance, assume that even if we know all the far fields or the near fields, what we can talk about for the resolution we can get. Of course, when we come to numerical methods, we usually only have like a few, if not many, like a few, or sometimes even one or two incidence field, and then still we want to get some reconstruction. And we have also some works along those directions, but that's another another front of work. In those cases, we may have methods that we can kind of identify the objects. And of course, even the uniqueness problem in those cases are difficult. Okay, so some of the objects that we will be using, in fact, you can kind of forget the definition, but we will be using some operators, which we will call the Neumann-Poincare operator, and we will understand the spectrum of that, and also the eigenfunction of that. And also we will understand some operators that some so-called coefficients, called the scattering coefficients or the generalized polarization tensor. We will have some general form in the slides later, but this is one of the first version, the simple version. Basically, you can forget the definition there, but you can keep in mind what is that it's described. So, or perhaps you can even take that as a definition. So the idea is the incidence modes, the incidence field can be decomposed as incidence modes. Okay, and for each of these incidence mode, when it hits the object, it's give you a bunch of scattered modes. So you can imagine that the incidence ray are like perhaps EI k dot x, somehow like that entering. Okay, and then you can have some sort of decomposition into incidence fields where those decompositions follow the effects that they come from the PDE without the inhomogeneous inclusion, and you can have some sort of decomposition. And then each of these modes will enter, and then they output a bunch of scattered modes. And these so-called scattering coefficients are nothing but just describing this kind of incidence to scattered mode transformation. So in that basis, they are this kind of matrix you can imagine that they are describing this. Okay, so if you have the U naught M mode enter, then you will get a bunch of the so-called scattered modes in the two-dimensional case. In the Helmholtz, you will get a bunch of Hankel functions times exponential of n theta. But you can also generalize in higher dimensions, where you will get still some Hankel functions, but different different n in there, and then the radial, the angular side will become, for instance, spherical harmonics and stuff like that. Okay, that's the high level idea. Some modes entering, and then some fields that scattered. And these are some of the objects that we will look into. And to make a better description of that, it is nothing but just that if you look into the far field, then you will realize that the far field pattern can have the Fourier transform, and the so-called scattering coefficients in those cases are just the Fourier coefficients. Okay, so you have the incidence angle, you have the scattered angles, and then you can do the decomposition. And you can imagine in high dimensional case, you can have the spherical harmonics again, and then you can label them using those bases. Okay, and then the so-called scattering coefficients in those cases are labeled with these labeling of spherical harmonics. Okay, and one of the key things is, in fact, the problem is severely ill-posed. So what does that mean? That actually one of the ways that we can say is that if you linearize a problem, the linearized operator does not have a bounded inverse. So you cannot actually even recover local uniqueness by directly applying the uniqueness in the linearized case. So a way that we can think of to quantify, of course, there are other fronts of doing that, but a way of imagining that is this inverse being unbounded operator. How do we quantify that? The so-called ill-posed-ness is, you cannot imagine that, suppose you're working in a numerical setting, you truncate it in a finite dimensional space using modes or using resolutions. Now, because it is unbounded, you can imagine that the norm grows as the truncation starts to, the dimension of the truncation starts to go higher and higher. And the growth or the speed of that growth would have some sort of quantification. And in a way, exponential ill-posed-ness, which is known in this community, can have one of these interpretation that the Fourier coefficients or the Fourier modes in here are in fact having more than exponential decay. What we can imagine is, suppose there's noise. The noise is like in the Fourier sense, kind of uniform across the spectrum. And the information that we can get for the physical quantities are having exponentially decaying tail, which means very quickly the noise will dominate and we will no longer be able to recover the fine details. If, for instance, the higher modes for the scattering coefficients are kind of reflecting the higher, the finer details, then that's what should happen. But whether it is true or not, we can imagine that the full recovery problem, if the norm kind of grow terribly, then it is very ill-posed. That's one of the way. That's not the unique way. There are other fronts of works that quantify very similar situation, but without using this language. But that's one of the ways to describe it. And if we use that to describe it, then the resolving power will then be the signal to noise ratio, which is given by, analyzing the signal to noise ratio given by this bounce that is exponentially decaying. Okay, so these are the, and that's the difficulty we run into, because basically the nice properties are kind of buried. Okay, so we look into several fronts or ways to understand or see whether we can get better resolution. One of the interesting phenomenon was Arp and other collaborators realized that there are some cases where high contrast target, which means the coefficients in here being suddenly very large as opposed to the background, okay, like a jump, okay, piecewise constant jump, perhaps you can imagine, okay. Then you would be able to recover the fine details of the scatter. Like I said, it shouldn't be expected because, like in the far field, you always expect things like half of the wavelength, because under the far field approximation, basically your measurements is more or less like a Fourier transform. So the wavelength would be determined by I mean, with the wavelength of the wave that enters would kind of determine how the resolution of your image would be like. Okay, but in some high contrast target, it seems to be breaking the barrier. One of the first works along these directions was to understand why. Okay, and in fact, the idea of why that's happening is very simple. We can go through that very quickly. It turns out that, again, well, one disclaimer, very important disclaimer. If you would like to understand uniqueness of recovery, none of the things that we are discussing along that direction should help, because many times we would linearize a problem in some ways and understand locally how the resolution is like. But as we say, the problem doesn't have a bounded inverse. I mean, the linearized problem doesn't have a bounded inverse. So that alone will not help us have good understanding. But in terms of resolution, on the other hand, and in terms of numerical approximation, that would give us some information or understanding of why these information in the far field would actually be kind of important from, for instance, fine details of the objects that you want to recover and how they are going to affect the measurements on the far fields. So one thing that we can imagine is some sort of perturbation or variational derivative. Then perhaps let's look into the scattering coefficients or generalized polarization tensor, and you perturb it a little bit and see if you can even identify such a perturbation, because if you cannot identify such a perturbation, there's no hope you can recover fine details globally. Okay, so let's look into that. And then we realize the coefficients, the so-called scattering coefficients, are nothing but the following. If you perturb it a little bit, you will see a coefficient multiplying the Fourier transform of the Fourier modes of the perturbation of n minus m. Which means if I perturb the inclusion a little bit, the far field pattern will give us a Fourier transform that is perturbed a little bit with this formula or this understanding that they enter as the following. I want to see how fine the perturbation goes like, then the Fourier modes are expressing how fine that is, that it's giving us. And this information enters the measurement. And if the coefficients in here are decaying rapidly, crazily, then we have no hope. In fact, they are, because right at the start, we remember this kind of more than exponential decay. And in fact, for the C coefficients, they are also similar. But now we realize something very interesting. We can rewrite these coefficients in terms of resolvent of certain kind of compact non-self-adjoint operators. That's fine, but there's something interesting. That's the resolvent has a parameter. I mean, the lambda minus, lambda I minus this operator. That lambda in there is now in the form of this, the contrast, the reciprocal of the contrast, which means if the contrast is high, the reciprocal of the contrast is very small, and then it will be very much like going all the way down to 0. And because this operator is now compact, that means the resolvent is getting very large magnitudes along some direction. Even though we know that this is not self-adjoint, and we know that the eigenvalues are actually complex. So if the contrast is real, there's no way you really hit the spectrum. Okay, so it's always having some distance, but it's kind of getting closer and closer. So the idea is now that if it turns out that these contrasts in some ways very, very close to some of those, as a spectrum of some of those compact operators, then it will turn out that the Fourier modes of n minus m kind of got boost up, and then you can measure them more clearly, not very clearly because it is still exponentially opposed. That is not a problem we can fundamentally change with this kind of understanding. Perhaps bubbling, perhaps fluidization, other directions might, but in our case, we don't have that. So we are still having exponential ill-posed-ness, but we realize that we are in a better shape. And a very quick analysis or understanding will then be that those eigenvalues are having some pattern, okay? And those patterns are like 1 over m plus 2l squared, so they are like following certain kind of integer lattice, but squared and 1 over of that. Which means, very interestingly, if we choose the, well, actually we cannot choose, but suppose we can, then the contrast inverse being some sort of pattern, like a certain integer times pi over, for instance, 1 over 2r, certain physical parameter, I mean certain radius, okay, minus some other constant square, which means it is one kind of pattern given a certain large k, then it will simultaneously be close to the spectrum of many guys. But once again, I have to make a clear distinction or disclaimer that we are not really hitting the spectrum, which means the resolvent is still well defined. Okay, but they are very close. And one single choice would be very close to simultaneously to a bunch of these eigenvalues or this spectrum. Okay, and that would kind of boost up the Fourier modes of the perturbation, for first order perturbation n minus n simultaneously for a lot of states. Okay, and that would kind of give us certain version of super resolution in a way. And we have numerical example of this kind of understanding that that's one example. If we have an incidence ray, and this incidence ray is actually having wavelength 2 pi, and this guy is smaller than 1/10 of 2 pi. Okay, so the circle in here that you see, the red thing, the circle in there, is actually less than 1/10 of the wavelength. So any perturbations or fine features like these kind of oscillations that you see on this boundary should not be seen. That shouldn't be expected to be seen. But somehow, if the coefficient of the that represent the contrast, which means it is like the subtraction of the inhomogeneous coefficient and the homogeneous coefficient is very large, somehow we have some sort of magic, okay, or coincidence that we might be able to recover these fine details. In fact, we see the scattering coefficient going like bumping up at some point, but not really having a high trend because the spectral behavior is kind of weird. You move and then you get close to some of the spectrum, and then you move and then it leaves, and then it comes close again and it leaves again. And now you also have, in fact, you also have countable many kind of compact operators. We have Km and Kn, so you have a bunch of operators that you move close and then you leave. So it's not like really a monotone thing, but you kind of having spike going up. And we realize that in a very interesting manner, when these coefficients grow and they hit the pattern of what I said, like certain integers times, times some pi or things like that and square, then we are in a good shape of recovering these fine oscillations. Even though we are not able to recover full, we are now able to recover some of those fine oscillations. And again, it is more than almost impossible if we think of that as being smaller than 1/10 of the wavelength. And worst of those oscillations in there is now way less than that 1/10 of wavelength. So we should not be able to, I mean, traditionally speaking, we should not be able to see that, but somehow we are able to. So that's somehow the one of the ideas that we might realize that some resolution limits can be broken through. And along that line, Professor Hongyu Liu and me are also looking into that direction, trying to understand more whether there are kind of localizations and stuff, and whether this itself can help image reconstruction. So that starts all these analysis, and then we will come to localized resolution analysis, which means, in fact, if I give you a shape and then I perturb it a little bit, I might want to see whether it is true that we can recover fine details at some parts of the scatter and not other parts of the scatter. So we want to kind of understand the resolution in a local manner. And Lastin and other collaborators, in fact, that's with Hongyu, that they realize that corner singularities will always give us good positive lower bound on the scattering, which means they kind of shine through the space and you obtain better information. And one of the things now that we want to do is we want to get a good quantification of these kind of local resolution. And we want to say that at high curvature points, we should be able to get better resolution. So let's get to some background material. That in fact, a way to understand it is through the understanding of the Neumann-Poincare operator. Why? It's because that the scattered field is nothing but the single layer potential acting on the resolvent of the Neumann-Poincare operator of the Neumann derivative on the surface of the inclusion. I mean of the incidence field of the inclusion. So if it happens that this resolvent is, I mean, even though it's well defined, if it is such that lambda is very close to the spectrum, then you hit large. Now the thing is, if we are in the traditional case, it is almost impossible because the spectrum is within -half to half. At the lambda that comes from the physical parameter is larger than half. So there's no way you can really hit the spectrum. But still, if some of the modes are kind of focused, perhaps we should be expecting a better reconstruction. Okay, and that's somehow motivating that front of analysis. And if we have good enough regularity, in fact, this Neumann-Poincare operator is nothing but a pseudo differential operator of order -1. And with the principal symbol that has the following form, you have a second fundamental form acting on Keji. In fact, that's in the geodesic coordinates. So in general, you will have G inverse A, G inverse inner product, okay? And the Keji now is on the cotangent space, okay? So, let's simplify everything. Just think of it in the normal coordinates. Then this is the second fundamental form, explicit curvature acting on the Keji, okay? And then there's some scaling Keji to the power -3, and then there's also a mean curvature term, okay? Which actually just comes from the trace of the A. So it's kind of interesting, this kind of structure that the principal symbol is having an explicit expression that comes with the second fundamental form, okay? And it is a compare operator. And more, I mean, what's more is that the scattered field, you can now expand it using incidence mode and reflected, so scattered mode, either in the case when the lambda, the epsilon in there is 0 or non-zero. In fact, there are very similar expansions. In the case when it is 0, that is generalized polarization tensor, and in the case it's not 0, it is the scattering coefficient. Anyhow, in the end, they are looking very similar, and you can also generalize it to arbitrary dimension. And then you will realize that those coefficients are always have these forms, that those coefficients are nothing but just some inner product, okay, on the surface of spherical harmonics and an operator acting on those spherical harmonics. And some of those operators does not depend on extrinsic curvatures and stuff like that, but there's one of the which has this this operator that in this expression that we have. Okay, so the operator has the principal symbol that has this guy. Okay, so the local resolution analysis are going to use this this property. In fact, you can also perturb it to look into the first order perturbation of those generalized polarization tensor or the scattering coefficient, and then you also have this expression there. Now, because of that, we are able to decompose, at least theoretically, this is not really a numerical reconstruction, but at least theoretically, into inversion processes, such that most other inversion processes are not related to the curvature. So they are somehow lower bounded and upper bounded by, but again, sorry, I will take it back. It's an unbounded immersion. So, but after you do a finite dimensional truncation, they will be lower bounded and upper bounded by like exponentially growing coefficients, but at the same time with the dependence of the coefficients on, like in striped circle and the diameter of the inclusion, those are somehow depending on curvature, but not entirely. What is more important is the local curvature information will now enter our reconstruction explicitly as follows. Now we have some inversion processes. Again, those inversion processes are not bounded inverse, just to clarify, but they are not very depending on curvatures. There's a little bit depending on curvatures, but they are not depending on local curvature information. And the piece that enters the local curvature information will go like the first order perturbation of the first order perturbation of your scatter times the mean curvature. Okay, so with that, we are able to do the following. Suppose the object is not too away from, for instance, an unknown object, we kind of perturb it. Then we realize that projection of the perturbation times the mean curvature is now somehow uniformly bounded, exponentially growing. Again, it's a ill-posed problem, so it is unbounded operator if we look into the infinite dimensional space. But in the finite dimensional truncation, it is growing exponentially. But those guys are not giving us local curvature information. What is giving us the local curvature information is what's happening at the left-hand side. The projection on the certain Fourier projection projected space is now bounded by this, which means if we really want to recover the H, we now at the end has to do the 1/over of this capital H, and that is when we see that the local curvature information is important. And in fact, these estimates will come to tell us that high curvature will now give us, high local curvature will now give us information that these perturbation entered the far field with a magnified quantity that you can measure. again, as I said, we are not breaking the resolution by saying that it is no longer ill-posed. It is not true. It is still exponentially ill-posed. But that is how we have this kind of estimate, both in the scattered case and in the case when we are in the with the generalized polarization tensor. Okay, now motivated with that, we also want to see how the plasmon resonance, which are in fact just the eigenfunction of the Neumann-Poincare operator in our study. There are other ways to understand what it means by plasmon resonance. This is one of the approximate model, and in fact, you can really hit those modes in the case when we have metamaterials. Okay, when some of the coefficients can go negative, you can hit them. But otherwise, those modes are not really going to shine out. Okay, but they still, again, affect our measurements by this kind of resolvent. Okay, so what we want to do is we want to understand those plasmon resonance mode, and we also realize that plasmon resonance modes kind of get higher energy, or kind of having some sort of concentration at the points or around the points with high curvature. And why that is the case, it comes from the fact that the operator that we previously looked into, where this Neumann-Poincare operator we have has the principal symbol that has the curvature. So first off, we can now look into the generalized Wells law, or in fact, there are other kind of LP or L infinity estimate, but we use the simple version, which is now telling us that in some average sense, the eigenmodes or the plasmon resonance around the point will somehow be more localized when the curvature is high, because the Hamiltonian, which is now given by this principal symbol, is having the curvature term in there. And the volume that we get from this integral in here will now have a ratio. If I have one point and I have another point, then these kind of averages depend on the ratio. Okay, and in fact, you can even have the pointwise Wells law using the heat kernel kind of estimates and the Laplace transform. But in our work, we just want to bring us the attention into the fact that this Hamiltonian having the curvature will give us many understanding. I mean, many different results of the understanding of how those eigenmodes should be concentrated. And one of the things is this generalized Wells law, which says, in fact, resonance modes are kind of concentrated in an average sense when they have higher curvature, because the volume at the right-hand side, the volume ratio will now be large if the curvature ratio is large. Okay, and we can even get, for instance, using the quantum ergodicity argument and using the Egorov lift of the Hamiltonian flow, that you can now say that there's a subsequence that it kind of that's the eigenmodes are kind of converging weakly to a guy where you can now compare the volume ratio. It's a little messy, this kind of theorem, because in general, we don't expect the Hamiltonian flow to be algorithmic, so you have to appeal to the extremal points decomposition or the the ergodicity decomposition theorem to rewrite that. But somehow you can imagine that is kind of converging to a certain ratio where, I mean, certain ways where those ways have a ratio depending on the curvature information. Okay, and in the case when it is algorithmic, we are happy. But of course, usually algorithmicity comes from hyperbolicity, so we don't write it that way. In many cases we don't have that, but we will very quickly see situations that we can have some algorithmicities on leaps. But anyhow, these comparison functions are depending on curvatures, because they are depending on Hamiltonians, and the Hamiltonian depends on curvatures. So we have lower bounds and upper bounds given by the extrinsic curvatures, not the intrinsic curvatures. Okay, the second fundamental forms and the principal curvatures. Now, if we want to have a better understanding, a way to make it happen is now that perhaps under some better assumptions, we really have a completely integrable system, or at least we have a better moment map to work on. And suppose we are in such a good shape, then you can now flow along these Hamiltonians and lift it in the lift it in the Fourier space, such that those guys are all kind of commuting. The operators are commuting, so we have a concept of joint spectrum. And then we'll realize that in fact the joint spectrum will also behave in such a way. So you can imagine that those joint spectrum converges to the moment polytope generated by the moment maps, okay, in a weak sense. And not only that, the ratio of the resonance modes, again in an average sense, will now depend on all the Hamiltonians that are commuting with our first one, which is the Neumann-Poincare, that is of the Neumann-Poincare operator. So we have nicer expressions. So they are now localized on the leaves, okay, on each of those fibers. And in those cases, we can write an explicit decomposition, which let's not come into detail, but what I would like to say is that in those cases, we can, for instance, suppose our shape has some sort of rotational symmetry and it's in 3 dimensions. So the surface is 2 dimensions. In that case, 2 Hamiltonians, 2 commuting Hamiltonians will be good enough. So a rotational symmetry will help us. And in that case, indeed, we will have the joint flow being ergodic on each of those leaves. And you can imagine your decomposition of the topologically the sphere bundle on this, the circle bundle on the sphere. You can imagine the two on the 2 sphere, and you can now decompose that bundle by toruses and S1s, and our flow, or the joint flow, is actually ergodic on each of these leaves. And because of that, we can now have a very explicit quantification of the lower bounds and upper bounds given by curvatures. And then again, higher curvatures will give us better concentration in here that the plasmon resonance are kind of localizing in such a way. Okay, I kind of seem to run out of time, so let me come to the last point very quickly, 2 to 3 minutes. There's another direction that we are also looking into, which is the so-called transmission eigenfunction, which is the case that when we have an object, you will realize that there are some possibility that certain incidence field and certain scattered field are coinciding, okay, with a certain particular chart. They're coinciding, which kind of mean that we have the Dirichlet boundary and Neumann boundary of the subtraction of the scattered field, the total field and the incidence field to be equal. Okay, so they kind of give us an idea of the so-called transmission eigenvalue problem, and that has been understood in the community like Cotton, Mock, Kush, and other people, and Carconi. Okay, but what we are focusing on is the understanding of the eigenfunction rather than the eigenvalue. And again, we seem to see some sort of localization or concentration on the boundary. And this is kind of expected in a way. Think of the case when you have those kind of total internal reflection, right? Suppose we now trick our objects by having an incidence field that is almost orthogonally hitting the boundary of that, then you can imagine that it is almost like bringing it along the surface, because otherwise it will enter, or the other side is if it is outside the angle, it is traveling out. If it is inside, it is totally reflected. So the differential optics approximation, suppose you have that, and we really hit that with the boundary case, then it just tangentially hits the boundary. That would be the weird situation that you don't really have this kind of a reciprocity. The reason being that it is not a good approximation. You always have ratio, okay? And but imagine this kind of situation that you can tune to that's almost angle, then somehow waves would kind of almost travel along the boundary, okay? And we can analyze that by looking into boundary integral operators. And again, we will realize that you can write that as a certain kind of integral operator where some of the operators don't depend on extrinsic curvature, but some of those operators will depend on extrinsic curvature. Okay, where you have now the second fundamental form. Of codimension one, so you don't have the K, you only have IJ. Okay, you just project on the normal direction. And then very quickly, let me take 1 more minute and then I'll stop here, which is that we now define an almost transmission eigenvalue, and which means they are not really transmission eigenvalue, but slightly deviating that, which makes perfect sense in numerics because you never know whether it is really the transmission eigenfunction or it is very close to it, or if the scattered field is very weak. Okay, we have this kind of definition, and then we realize that they are again having some sort of localization, and also that it is very interesting that the zeroth order, the highest order will now no longer depend on the curvature, but the next order will have some resemblance of the high curvature, which means if we don't push your Fourier to really infinity, curvature term will still enter in a weird way, but in a weak way. Now, in the end, I would like to show some of those localized resonance modes as we see, okay, as numerical examples. And then there's a method that we can use using this kind of localization that we can recover an object. And I think I'll have to stop here. I kind of overrun a little. Okay. Yes.
Yes. Thanks, Yating, for this very interesting talk.
Thanks.
And so we'll welcome to all the questions from the audience. And so if you would like to ask questions, you can unmute yourself and ask Yating directly.
Okay, that's great. Yeah, and I put the slides, the last one.
Yeah, I think that the talk is extremely technical.
Oh.
Okay, good. Yeah.
Hi, I think nice talk. Yeah. So I want to know in the first part, you gave a sensitive analysis with the shape, right?
Yes. Yes.
So your results show that the Fourier coefficient is very sensitive.
Yes.
I mean this corollary. How to explain the quantity C here? Can you explain?
Okay, so the quantity C here is in fact the following. We imagine that, so the physical explanation is like this. Suppose you now have the measurements, and now you perturb the scatter, or in the conclusion a little bit, then the perturbation direction H will now enter your measurements, and we do the Fourier transform. And again, we expect the Fourier to be uniform, to have uniform noise, because it's like the white noise, then Fourier spectrum will have a constant. Then the perturbation direction will now give the Fourier modes, and you will have exponentially decaying C's that multiply to it, and then we measure it. So our measurement will have certain exponentially decaying guys multiplying the Fourier modes, okay? And that means we are not really able to get the Fourier modes, especially when the Fourier modes are of very high modes, which means if the perturbation has very fine details, they should not be very clearly shown in your measurements because you have the noise. now the C in here are behaving as follows. We now have the N and M's, and we have the resolvent of M of a certain compact operator acting on a Bezoar function or special function, and another resolvent of order N acting on the another order of special function. And you multiply these two guys together, and you also have the contrast inverse. So now suppose we have the contrast, which is the epsilon star in here, very large. 1 over that will be very small. Like what we have discussed before, the operator is compact but not self-adjoint. So you now imagine, we can now imagine the spectrum having, actually we will know that the spectrum is like real part larger than 0, all the way exponentially going down to 0, hitting the real line. But you are traveling on this line. So you are not really hitting the spectrum, but in some cases you are close to the spectrum. And what turns out to be interesting is that there are some contrasts such that you can be close simultaneously to a bunch of those K. So Km for a large amount of M. And what that means is all those CMNs are now going to be boosted up. And that means what you can measure in from afar are now way more clearer, because you now have the C multiplying the Fourier coefficients. So if the Fourier coefficients of that higher modes can be better seen, even with a same level of noise, we can better recover the finer details of H, which means we can recover the finer details of the scatter. That's what it means by this corollary.
Okay, thank you.
Thanks.
Yeah, you see that fixed frequency. For fixed frequency, this problem is very ill-posed.
Yes. Yes.
If you use a multiple frequency, can you?
Yes. Yes. Definitely. Yes. Yes.
Okay.
If you have multiple frequency, it's a way better post problem. Yes. Yes.
Do you have a mathematical analysis for the aspect?
We've currently focused on the fixed frequency analysis, but indeed we can definitely work on the case when we have multiple frequencies. Yes. Okay. It's because we know that the fixed frequency guys are the more difficult ones. So when we look into the resolution analysis, we want to do that. In fact, we can imagine, for instance, because the point spread function in the 2 dimension are like the Bezoar functions of the 0th order. Now, if you have multiple frequency, you can massage your point spread function by certain kind of transform, right? You can multiply J0 of K R. Now you can massage that with the K times another function. You can now change the form and squeeze. And numerically, what you can do is you can find the best function such that it can be massaged into. And you can now boost your resolution up to like 5 to 10 times. That's something we have done along on that kind of reshaping with Keji and Professor Jun Zou. Yes. That's something we have known. And of course, most of multiple frequencies in the case, I mean, from an analytical perspective, you can now do analytic continuation along the frequency direction. So you now don't just have one direction to do this kind of continuation. You have 2 directions. Things are way better. Yes.
Thank you.
And I remember actually Baogang's one of the work has also discussed that. But I forgot.
Yeah. Yes. In your numerical experiment, you add a noise on the far field pattern.
Yes.
Do you have an experiment with respect to the perturbations on the shape?
Yes. So you mean numerical experiment, right?
Yeah.
Okay,
you add noise on the far field pattern, but your analysis is with respect to the shape.
Yes.
Yeah.
So what we were doing is we now have a shape which is a ball, and then we perturb it with high Fourier modes, and then we want to see whether we can recover this perturbation. Yes. And the shape is now with cosine 3 theta, cosine 6 theta, cosine 9 theta, and they are oscillating. And yeah, and we see that the scattering coefficients are really having this kind of behavior we're having, and then we want to recover the perturbation of the shape. And it turns out that we can succeed to recover even the 9th Fourier modes, even though it's like tiny bits of oscillations. We can recover that, which is surprising because it's even the ball itself is smaller than 1/10 of the wavelength. Now, these oscillations, I probably would expect that to be smaller than 1/20th of the wavelength. So that's very surprising that we can see anything rather than just 1 point. I mean, 1 bulk.
So the high contrast help to enhance the resolution, right?
Yes.
From the physical review, you mean the high contrast can make the wavelengths be smaller?
Excuse me?
The high contrast can make the wavelengths be smaller inside the inclusion. So maybe
might be. Yes, actually, it is one of the things that Hongyu and I are going to try to figure is that we kind of also expect some sort of localization resonance modes also in the high contrast case as well. Yes. Yes. But again, this front, I mean, unlike what we discussed later, this front is kind of funny because we are saying that a priori, if we know there's high contrast, then we can recover fine details. But the inverse problem is to recover what's going on. So we should not be able to tune what's inside. Except, for instance, if we put in an additional inclusion, or now we kind of put a certain background into it, for instance, a random medium with high contrast, then of course this will probably be helping. But those are like super focusing, or perhaps you can throw in bubbles and you can do bubbling, right? So those are some of the things that we can also think about. But this is one of the very interesting thing, that even if we don't do anything with high contrast, at some points we accidentally have super resolution, which again is probably related to some resonance modes being localized.
Okay, thank you.
Thanks.
For your second part, is your dimension is greater than 2.
Yes, greater than 2. Yes,
yeah.
Because when it is 2, it is of Cauchy type. It is log type singularity, and all the analysis will be different. But otherwise, it's going to be so differential operator of -1.
Okay.
So many of the works are hinging on the fact that the non-Poincare operator is a so differential operator of -1. But if it is dimension 2, it is log type singularity. It's of Cauchy type. Yeah. So things are different. But whether it is going to be having something similar, perhaps we have that. In fact, I believe many people will have worked on 2-dimensional case because you can parameterize over curve and just do the expansion there. For instance, I remember like Habib have worked along those directions in those cases.
Okay. Thanks for your talk.
Thanks very much.
Thanks for the questions. And so any other questions from the audience? Okay, so if no, I think the time is up. Yes, so it is over 4 p.m.
Thanks very much.
Yes, and I think it's also very late for you. Right now it's over midnight. Okay, so I think maybe for the talk we end here. Yes.
Okay, sounds great. Thanks. And yeah, if you have other questions.